So we want to look at subspaces, and we're going to start by looking at subspaces of Rn. The important thing to remember is that a subspace H of a vector space V is a subset of V that is also a vector space. Whenever we talk about a generic vector space, we can always think about Rn, because we're going to learn techniques to make every vector space look like Rn. That's why Rn is the primary one that we need to study. The other important thing to note here is that a subspace has to be a subset of V. So the other important thing is that where H is a subset of V. That means every element of H is also an element of V. So a subset means that every element not elemento, every element of H is also an element of V. So every element of H is also an element of V. This is important to recognize because a lot of us are getting a little bit casual and we want to start thinking about dimension. You're going to keep looking forward and you want to say that it doesn't, so the columns of a matrix don't span R3. There's two pivot columns, so it spans R2, but that is not the case. Elements in R2 are not in R3. So this is the most important thing. R2 is not a subspace of R3. R2 is not a subspace of R3 because R2 is not a subset of R3. R2 is not a subset of R3. Elements in R2 are not in R3, so R2 cannot be a subspace or a subset of R2. An element in R2 looks like 5, -3. An element that looks like 5, -3 is not an element in R3. Two elements, or two entries. And vectors in R3 will look like 5, -3, 4. 3 entries. R2 is not a subset of R3. Any questions? All right. Now, when we have the span of two vectors in R3, we do get a two-dimensional subspace of R3 that is not equal to R2, but isomorphic to R2. So we'll have to talk about what isomorphic means. All right, so there's a lot of definition, and a lot of the homework problems are about concern understanding that definition. But let's do the Cliff Notes version of things, or let's say this, I think they're the Spark Notes now. A subspace is the span of a set of vectors. The span of a set of vectors is a subspace. The span of a set of vectors that is the set of all linear combinations of those vectors is a subspace. This is the important thing that we need. The span of a set of vectors is always a subspace, and a subspace is always the span of a set of vectors. So if H is a subspace of V, if H is a subspace of V, then H is the span of a bunch of vectors from V. Or a bunch of vectors from H, but they're also in V. So if H is a subspace of V, then H is the span of a set of vectors where all those vectors are in H. So this says where VI, I indexed since there's P of them, VI is in H, is an element of H for all I. So this symbol is an element of. Or if we're being casual, in. And this symbol is for all. So, so all these vectors are vectors in H. The span of that set of vectors is how we describe the subspace. So when we want to describe the subspace, we need what we're going to call a spanning set. So the set of vectors is called the spanning set of H. So we'll call that a spanning set. That set of vectors spans H. So we use span as a noun and as a verb. When we use it as a verb, the set of vectors spans the vector space. So the subspace or the vector space. The set of vectors is the thing that does the spanning. We say the set of vectors spans the subspace. The subspace is spanned by the set of vectors. No. In this case, there are P vectors that are spanning H, but H has an infinite number of vectors. So the set of vectors that does the spanning is finite, unless the vector space is infinite dimensional. But what I have here is I've listed a finite set of vectors. There are P vectors in this set, and it's a spanning set for H. So the vectors do the spanning, the space is spanned by. So the spanning set, the vectors span the vector space. The set of vectors span the space. So look at what the subject of that sentence is. The set of vectors is what's doing the spanning. The the space is spanned by the set of vectors. Usually, there are infinite dimensional vector spaces, but usually, while we're practicing, we're mostly going to be focused on finite spanning sets, but that's correct. There's an infinite number of linear combinations of the vectors in H. So H has an infinite number of vectors, but the spanning set, in this case, has a finite number of vectors. So this is a finite number of vectors in the spanning set. But since H is the set of all the linear combinations, the space has infinite number of vectors. Because H is the span of that set of vectors. So it's the set of all the linear combinations of those vectors. That makes the subspace, infinite. The spanning set, for our purposes, will usually be finite. Any questions? All right. So we have a spanning set of vectors for a subspace. What we want to do with the spanning sets is take it down into a basis, which is a linearly independent spanning set. We want to refine a spanning set into a basis. So, a basis is a linearly independent spanning set. A basis for a subspace is a linearly independent spanning set. A basis for a subspace is a linearly independent spanning set. Because we want to write everything in the space, we want to write everything in the subspace as a unique linear combination of the vectors in a basis. Yes, there can be more than one set of spanning vectors defining a subspace. There are an infinite number of bases for any vector space. So a basis is a subspace for a subspace is a linearly independent spanning set. The reason that we want a linearly independent set is that we want to describe everything in the subspace as a unique linear combination of the vectors in the basis. So the reason for this, we want the linear independence because that gives us uniqueness. Spanning set gives the spanning part gives us existence. Linear independence gives us uniqueness. We want to describe every vector in the subspace as a unique linear combination of the basis vectors. We want to be able to describe every vector in the subspace as a unique linear combination of the basis vectors. So we want to describe a subspace with a spanning set. We say these are the things that you need to build the set, the space. So once again, the spanning set is the set of vectors that you need to just build everything in the subspace. We want to whittle that down to a basis. We want that set to be that spanning set to be linearly independent so that everything in the space can be described as a unique linear combination of those basis vectors. This description we'll call the coordinates of the vector relative to the basis. So we want to be able to describe everything as a unique linear combination of the vectors in the basis. And we will call those the coordinates of the vector relative to the basis. Any questions? Let us stop and do an example. Oops, I don't have my example ready. Any questions before we do our example? How's everybody doing? So I'm going to write down a set of vectors, and I'm going to say define a subspace as the span of that set of vectors. So let's look at an example. Let's let H be the span of V1, V2, and V3, where V1 is this vector, 1, 2, negative 3. V2 is the vector 2, negative 5, 6. And V3 is the vector 8, negative 11, 12. So H is a subspace because H is the span of a set of vectors. What is H a subspace of? Where do all these vectors live? R3. These vectors are all in R3, so we would say H is a subspace of R3. Since H is linear combinations of vectors in R3, everything in H will just be a combination of these vectors in R3. So H is a subspace of R3 since the vectors in the spanning set V1, V2, and V3 are in R3. I don't want you to think it's because there are 3 of them. Well, we're not sure if H is the same as R3. This is a spanning set, and there are 3 of them, but we don't know that this is a linearly independent set. This is a spanning set, but we want a basis for H. So this is a spanning set that's a spanning set, but we want to try to find a basis. So let's suppose we want to find a basis for H. Let's suppose that we want to find a basis for H. And let's find out if H is in fact all of R3, or if H is some smaller dimension subspace of R3. So let's find a basis for H. To find a basis for H, we need a linearly independent spanning set. So what tool could we use to find a linearly independent spanning set? What do you think we're about to do? Anyone want to guess? Matrix. And we're going to find the RREF of a matrix. And the columns of the matrix are just going to be these 3 vectors. We're going to see if this set of vectors, when we put them in a matrix, has a pivot in every column. If these 3 vectors have a pivot in every column, then we have a linearly independent set. We actually don't want an augmented matrix. We're just going to write a matrix. Because we're not going to try to solve the equation AX equals B. We're just going to see if A has a pivot in every column. So I'm going to take the matrix V1, V2, V3. That matrix is equal to, now I want to be very careful here about using my equal sign. So my numbers look like this. So V1, V2, V3 is equal to first column V1, second column is 2, negative 5, 6, and the third column is 8, negative 11, 12. Now, I want to find the reduced row echelon form of this matrix to find out where the pivots are. But I don't want to use an equal sign because you don't want to say that a matrix is equal to its reduced row echelon form. That's why I usually write an arrow here. And then sometimes in tests and stuff, I wrote like a tilde, like a little swoosh. But we're going to find an RREF. We definitely do not want to use an equal sign because these two matrices are not going to be equal. So let me take a minute and find the RREF. I can see this right away. And I'm going to find out what the third row looks like. Let's see. I was doing movie typing there. The third row is a third column is 2, 3, 0. So we can see that we're not going to get all of R3. There are only pivots in the first two columns. Remember, the pivots of this matrix are the same as the pivots of the reduced row echelon form, but if we want to say this set of vectors is not linearly, I keep saying not linearly independent. We want to say this set of vectors is linearly dependent because the matrix does not have a pivot in each column. We don't want to say this set of vectors is linearly dependent because the reduced row echelon form has a pivot in every column. When you say it that way, you're implying that you think the pivots of the reduced row echelon form and the pivots of the matrix are going to be different, and that's not the case. We use the reduced row echelon form to find the pivots in the matrix. But there's a pivot in the first row, first column, and the pivot in the second row, second column of the matrix, and all of its row equivalent forms. So don't say because of the reduced row echelon form. The reason that, even though that's what you're saying is true, it's implying that you don't understand something. Why did you include this reduced row echelon form? You want your statements to be efficient, so you're not saying extra stuff, because that could be interpreted by, you think that it's important to say reduced row echelon form. That's why you wrote it. Does that make sense? It's really important that you don't say the reduced row echelon form has a pivot in every column, therefore this set of vectors is linearly dependent or independent. So it's the matrix that has the pivots. The reduced row echelon form is just what we use to find those pivots. So what we see is that V1, V2, V3 is not linearly independent. So we can see that the set of vectors V1, V2, V3 is not, why do I keep saying not linearly independent? Is linearly dependent. But if we remove vector V3, then we'll just have vector V1 and V2, and that set is linearly independent. So this set is linearly dependent because we can see that V3 is a linear combination. Oops, that's not V3. V3 is a linear combination of V1 and V2. Free variable in what equation? No, that's making it worse. So you don't want to bring up free variables because we never brought up an equation here. And that was the other thing that comes up a lot. Non-pivot column is something that we could say because we're looking at a matrix. But as soon as you start talking about free variables, you're talking about an equation, and we don't have an equation here. And that's why I was taking off points when you were invoking free, when lots of you were invoking free variables when there was no equation in play. You were looking, all we had to look at was a matrix. All we can talk about is pivots or a set of vectors. Free variables happen in solution sets to equations, but there's no equation here, so we do not want to talk about free variables. Are there free variables? If this is an augmented matrix, then there are no free variables, right? Because V3 is exactly 2V1 plus 3V2, no free variables. if this is the coefficient matrix, and then there's a column over here, then the solution set to the linear system corresponding to that augmented matrix will have free variables. So do not explain things with free variables. Explain things with pivots when you're looking at a matrix. All we get to explain when we're looking at a matrix, the only justification that we have is the pivots. If there was an equation, then you could say the equation v1, v2, v3 times x equals b is not consistent for all b in R3, because this matrix doesn't have, because the solution set to v1, v2, v3 times x equals b has free variables. And that says there is an infinite number of solutions. But if you said it that way, I would still say, how do you know? Because the reason that you know that is that the coefficient matrix does not have a pivot in every row or column, depending on what you're trying to determine. So, to be clear, linear dependence occurs when the set of vectors as a matrix has a non-pivot column. So don't say free variables when there's no equation in play. So this set of vectors, v1, v2, v3, is linearly dependent. But if I get rid of v3, so since v3 is just 2 times v1 plus 3 times v2. So that tells me I can get rid of v3. If we eliminate v3 from the set, then we will have a linearly independent set. So we can see that v1, v2 is a basis for H. It still spans everything, the same things as the set v1, v2, v3, but this is now a linearly independent spanning set. So what we're going to do is we're going to look at a spanning set, and we're going to cut it down to a basis. Any questions? All right. So let's look at a vector in this subspace H and see. Yes, we could have picked v1 and v3 for the basis, because that would also be a spanning set. We could also use v2 and v3. We're just making the set of vectors into a linearly independent set by casting out the non-pivot columns, the ones that correspond to non-pivot columns. How's everybody okay? All right. I don't mean to jump so hard when you start saying including wrong things, but for me it's very dangerous to start talking about R2 as a subspace of R3. That's kind of the idea that gets the idea across, but it's not technically correct, and it's really important to be technically correct. And so when I see people referring to things like free variables, to me, we just got in the car and you didn't put your seatbelt on. And that freaks me out a little bit. Michael, come on, man, put your seatbelt on. Yeah, and I try to sound more nice, but I'm like, oh, that's dangerous. So, you know what I mean? So it's not because I'm looking for opportunities to be mean. I'm just naturally that way. It's just that those kinds of things could lead to misunderstandings later on. And so that's you not putting a seatbelt on. I'm like, oh, whoa, 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 we got to put our seatbelt on before we get going. Any questions? All right. I think all of you probably grew up just naturally putting on seatbelts, just like as part of your reaction. But I want you to know that that is 1 generation old. So when I was born, it was not a normal thing to just automatically put your seatbelt on. My generation had to be taught to put their seatbelt on as a change from a habit that we had before. It's really weird. And that is probably the closest analogy I have to people refusing to wear masks, because people used to just refuse to wear seatbelts. I ain't wearing a seatbelt. Can't tell me what to do. And then they get thrown out the front window of the car. And that's one less person that we have to worry about. But with this mask thing, you ain't wearing a mask. Then all of a sudden, I ain't wearing a mask. Can't tell me what to do. Blah, blah, blah. Now you're going to kill someone else instead. So that's what makes it a dick move. Anyway, so let's look at a vector in R3 and see if it's a vector in H. So H is still the span of the vectors 1, 2, -3, 2, -5, 6, and 8, -11, 12. H is still this vector space, or this subspace that we're looking at. And this is not a basis because this third vector we don't need. The standard thing to do would just pick the ones that correspond to the pivot columns. We can pick any two from this set, but just pick V1 and V2. Pick the ones that correspond to the pivot columns. So choose the pivot columns of the vector V1, the matrix V1, V2, V3. Just choose the pivot columns. Don't be fancy. Don't be like, oh, I'm not like other linear algebra students. I want to pick V2 and V3. I'm not like the students. I'm going to pick V1 and V3. Even though they are they'll give you exactly the same, the same subspace. Just pick the pivot columns. Just pick the pivot columns. I know you're going to be like, oh, you can't tell me what to do. But in fact, I'm the teacher. I get to decide what's what. So yeah, I do. But you are correct in observing that any two will serve as a basis. So the set 1, 2, -3, and 2, -5, 6 is a basis for H. We often like to give a basis a name, and we use like script letters. So B is these two vectors, 1, 2, -3, 2, -5, 6, or V1 and V2. That's a basis for H. Everything in H is a unique linear combination of these two vectors. So they inherit their names from the previous page. So every vector in H is a unique linear combination of V1 and V2. We know we get every vector because this came from a spanning set. Every vector, because spanning set. Unique, because linear independence. Not every vector in R3 is a unique linear combination of these two vectors, because not every vector in R3 is in H. So not every vector in R3 is a unique linear combination of V1 and V2, because not every vector in R3 is in H. H does not include everything in R3. I've only got 2 vectors in my basis for H. I could not possibly get everything in R3. Everything in R3 can only be described as a unique linear combination of 3 linearly independent vectors. So if I give you a vector, a question that could come up is this vector in H? So I'm going to do that. So let's let x equal the vector -2, -13, 18. So this is just some generic vector in R3. We don't know if it's in H or not. We have to check. So is x in H? That is x a linear combination of V1 and V2? That's the equivalent question that we have here. Is x in H? That is x a linear combination of V1 and V2? That's what that question is asking. How are we going to determine if x is a linear combination of V1 and V2? What are we going to use? What's the only thing that we have? In this case, we'll use an augmented matrix and then find the reduced or echelon form. In this case, we are going to be using an augmented matrix because I'm saying, is this vector x a linear combination of V1 and V2? So I'm going to consider the augmented matrix. V1, V2, and then I'm going to put x over here. So that's going to be the matrix 1, 2, -3. Oops, I dropped off the bottom of the page. And then 2, -5, 6. And then -2, -13, 18. And I'm going to find its reduced row echelon form. I know that that's what happens. Augmented matrices correspond to matrix equations. We're actually looking at a vector equation. So we're actually considering is, x would be bad. C1 V1 plus C2 V2 equal x consistent. So I hate to be that guy, but it's like, actually, we're looking at a vector equation. But yeah, matrix equations, augmented matrices correspond to matrix equations, but they are not themselves matrix equations. So we wouldn't want to say they are matrix equations. So I need to do some, oops, I need to get my window back. So I'm just going to punch this. I don't know what this last column is going to be. I know what the first two are going to be because I've reduced that before, but I need to go use my calculator. So and I find out that the last column is going to be -4, 1. Tell me what this last entry is. As soon as I wrote -4, you knew what this third entry is going to be. What's the third entry going to be? It's got to be 0 because we know that there's not going to be a pivot in the rightmost column of this augmented matrix. Once I wrote a -4 up here, well, clearly I can't have a 1 down here because in the reduced echelon form, that 1 would have zeroed out the rest of the column. So what we get, the augmented matrix of the vector equation does not have a pivot in the rightmost column. So the augmented matrix does not have a pivot in the rightmost column. Therefore, the vector equation is consistent. And therefore, X is a linear combination of V1 and V2. Therefore, X is in H. So the augmented matrix. Oh, look how badly I planned that out. I'm way at the bottom of the page. So stay tuned for conclusions. The augmented matrix does not have a pivot in the rightmost column, in its rightmost column. The augmented matrix does not have a pivot in its rightmost column. Remember, we only talk about the rightmost column of an augmented matrix. The augmented matrix does not have a pivot in the rightmost column. Therefore, the vector equation C1v1 plus C2v2 equals X is consistent. The corresponding vector equation is consistent. Therefore, we don't need to write all of this down in our explanation. I'm just saying all the different things, because I'm a big proponent of at least thinking all the things when we're practicing. So therefore, X is a linear combination of V1 and V2. In particular, we can see from this solution, X is equal to negative 4V1 plus 1V2. So we can say that yes, X is in H. Therefore, X is in H. So when I ask the question, is X in H? I'm asking, is X a linear combination of the basis vectors for H? And then we looked at a matrix equation. So is X a linear combination of the vectors in the basis? That's asking, is a vector equation consistent? And then to answer that question, we used an augmented matrix. Any questions? How's everybody, okay? I got two more things. There are two vectors in a basis for H, so we'll say that H is a two-dimensional subspace of R3. Since there are two vectors in a basis for H, since there are two vectors in a basis for H, since there are two vectors in a basis for H, we say that the dimension of the basis is 2. So this is the dimension of H. If I'm defining this term by counting the number of vectors in a basis, this implies something that it's very important to recognize. If I can call this the dimension, if this is a well-defined term, that means any basis for H has two vectors. So the number of vectors in a basis is going to be the dimension of the vector space. So in this case, the dimension of H is 2. What's consistent? So in this case, I just want to know if X is a linear combination of V1 and V2. We already know that since the matrix V1, V2 does not have a pivot in every row, C1, V1 plus C2, V2 equals B is not consistent for all B in R3. Because remember, it's not just consistent, if A has a pivot in every row, then AX equals B is consistent for all B in Rm. That's an important part of it. We just don't just say consistent, inconsistent, unless we're talking about a particular equation. I can say that this particular equation is consistent, but this matrix does not have a pivot in every row. So V1, V2 times X equals B is not consistent for all B in R3. But it is consistent for this choice of B. Does that make sense? This is why we can't, this is one of the things that makes linear algebra more difficult than classes we've seen in the past. We have to be very clear as to what we're looking at and what we're trying to say. We can't just look at things and copy what the answers look like. If you think about it, we started to get this kind of thing back in Calc 2 when we were looking at convergence of series. Sometimes we're looking at a series and we say the limits of the terms, the limits as n goes to infinity of something is equal to 1. And we can say since 1 is a non-zero constant, both these series converge. Sometimes we look at the limit as n goes to infinity of some quantity or some expression is equal to 1. Therefore, we can make no conclusion because we were doing a ratio test. Does that make sense? We can't just say if the limit as n goes to infinity of something is some number, then make a conclusion. That doesn't tell us. We have to know the context that we're working in. So this equation is consistent. Not every equation will be consistent because this matrix does not have a pivot in every row. That's a great question. That's absolutely the kind of question that needs to happen while we're working through these things. So I could point out all the crazy things that we might have to be careful of saying. Every time you write it, this is one of the things that's so exhausting about this particular subject. Every time you want to try to write a sentence explaining what's going on, you have to think, did I include all the words that I need to include? Did I exclude all the words that I needed to exclude? So it's like, oh, you got to get everything to get all, did I get all the necessary stuff? Did I cut out all the stuff that I don't need? Just kind of like go for that intersection. Go for that intersection. It's one of the reasons that it's very helpful to use the explanations like at least one versus at most one, but to recognize that at least one means 1 or infinity in the linear algebra case. At most 1 means 0 or 1. Each of those things include 2 of the 3 possibilities that we have for the solution set to a linear system. So the dimension of H is 2. The dimension of a vector space is the number of vectors in a basis for the vector space. The X that we chose is a unique linear combination of the vectors v1 and v2. So that's because X is in the vector space H, and so X is a unique linear combination of the vectors in this basis, this named basis, which is these 2 vectors in this order. So we can say that the coordinates, so basis B, is v1 and v2. All right. So X is in H, so X is a unique linear combination of those vectors. X is in H, and X is negative 4 v1 plus 1 times v2. So we can describe X as a unique linear combination of the vectors in the basis. So since this is the basis that we're using, we can, instead of saying X is negative 4 v1 plus 1 v2, we can do the linear algebra thing and say, ugh, that is too much to say. Can't I just say negative 4 and the 1? And the answer is yeah, we totally can. So we'll say that the coordinates of X relative to B, the coordinates of X relative to B the coordinates of x relative to b. So we're going to say the coordinates of x. And if I want to say, I'm going to describe x as a linear combination of the vectors in b, I put this in brackets and I make a subscript b. And I say the coordinates of x relative to b are -4, 1. So this expression here, this symbol here says the coordinates of x relative to b, that's a subscript b, and it's -4, 1. There are two coordinates in the coordinates of x relative to b because H is a two-dimensional vector space. Two coordinates, because the dimension of H is 2. Two coordinates. Since the dimension of H is 2. To describe X itself, X is in R3, so X has 3 coordinates, but relative to the basis, the standard basis for R3. But X has 2 coordinates relative to the basis B for the two-dimensional subspace H of R3. Any questions? What this means is that everything in H can be written, since everything in H can be written as a unique linear combination of the vectors in the basis, H pretty much looks like R2, but is most definitely not equal to R2. We can use a coordinate map to make H look like R2, but H is definitely not equal to R2. And that's the thing when on your tests I said, X is in R3, not R2, or X is in R2, not R3. Any questions? So since H is two-dimensional, we can use a coordinate map to make H look just like R2, but H is not equal to R2. So I'm going to write that sentence down. A coordinate map makes H look like R2, but H is not equal to R2. Because vectors in H have 3 coordinates, and vectors in H have 3 coordinates, because H is a subspace of R3. X is this vector. What was it? -2, -13, 18. That is in R3, not R2. If you want to, when things are equal, they have to be exactly the same. I couldn't say that -2, -13, 18 equals -4, 1. Those things can't be equal because they are not exactly the same. That's what equality is. We are working with a different kind of equivalence relation called an isomorphism. That's for later. But when you say one thing is equal to the other, that means they have to be exactly the same. Any questions? The coordinates of X relative to B are -4, 1. See, since X is a vector in R3, I need 3 pieces of information about what's going on. I need the first coordinate, second coordinate, third coordinate. When I describe X as coordinates relative to B, and it looks like a vector in R2, because the coordinates are a vector in R2, I have 2 pieces of information, but there's the third one, coordinate B, the basis B. If we were to draw a picture of H, H would be a plane in R3. But that is definitely not the same thing as R2. That plane we could take R2 and impose R2 on that plane by making a coordinate map. But that does not make that plane equal to R2. A plane in R3 is not equal to R2. It is super close to R2. In fact, I can think of it as R2, but they are most definitely not equal. Everything in that plane still has 3 coordinates in R3, not 2 coordinates in R2. That make sense? This is a lot to think about. So a coordinate map makes H look like R2, but it's not equal to R2. The vectors in H are actually vectors in R3. We write their coordinates relative to a basis. Yeah, it's about the space that we're sitting in. We're sitting in R3. We write the coordinates relative to a basis, and we only have 2 coordinates because H is a 2-dimensional subspace of R2. Sorry, a 2-dimensional subspace of R3, but that does not make it equal to R3. Isomorphic is not the same as equal. Any questions? Okay, let's pause the video here and maybe talk about some homework problems. Pausing video.